Okay, so this one right here. So use Cauchy integral to evaluate the integral, and this right. So you're looking at this integral. It's integral right here. 0,3 of dz over. You can factor the denominator into z minus 4 and also z plus 2, right? That factors into those two. Okay, so at 4, so this function has problems at 4 and at -2. That's where it has problems. This curve here, this circle, has radius 3, so it's going to be like this. So you're integrating around that. So this is the only problem point, really, for this integral. So what you want to do is you want to look at it this way. Where this right here in the numerator is kind of like your, this is like your f of z from Cauchy's integral formula, right?
Yes.
Okay, so that means that the integral is going to be equal to 2 pi I times f evaluated at -2. That's according to Cauchy's integral formula. And so you have 1 over -2 minus 4. So that's 2 pi I times -1/6. Negative pi I over 3 should be the answer. Okay, so does that answer your question?
Yes, sir. Thank you.
Sure. Now, if we had, there's different situations that we could have had. So there's 5 right here. Well, I guess number 35 was to just do it using partial fractions, right? And then that one partial fraction would have been 0. The one corresponding to, so you split up into a over z minus 4 plus b over z plus 2. And this one would just be 0 over that interval. Okay, was there any other questions on any previous homeworks or anything?
Number 26.
Also on chapter 4?
Yes.
Okay, so number 26. Wait, 26. This one wasn't assigned. This exercise wasn't assigned, and I don't really want to go there.
It was assigned on the homework.
It's assigned on the homework?
Yeah.
Yes.
Oh, no. How about, whoa, okay. So, actually, you don't need to do it.
Okay.
Yay.
Yeah. Okay, great. That's a
So,
headache
let me get this,
number.
hold on, let me get this straight as far as what's assigned. So this is not assigned, okay, but 27 is?
Yeah. and 28
28 and 29.
34. Hmm?
You have 29.
wasn't there.
Okay, so that's where it's off.
We need to do 29.
Yeah, so 29 is what you need to do. You don't need to do this one. Don't need to do 26. That's just going to be too long.
There
So
was-
27
so-
and 29 instead of 26.
Okay.
And then there's also 35 and 36. Okay, so
So we don't do 34.
34 is not assigned?
Yeah.
It is assigned.
34
What
was
about-
assigned.
No, what about 37? Is 37?
It is not.
It's not assigned.
We need to do 37.
So we don't do 34 and do 37?
Yeah, you don't need to do that one.
Oh,
Okay, so you know what? Okay, so here's the thing. I would appreciate if you do 37, but you know, wasn't assigned, so if you don't do it, that's fine. But you need it to do well on the exam.
okay.
Okay.
Makes sense.
Everything got.
So no 34, just to make sure.
Yeah, you don't have to do 34.
Okay, no 34.
Oh no. I gotta change. Let me go change. This is on Canvas, right?
Yeah.
Okay. Oh no. Let me go edit it right now. So that should be 27, 28, and 29, and then you should do 35. Oh. 36 and 37.
Okay. Try.
Okay, so people have already submitted. So someone already submitted the homework. Uh-oh.
Gosh.
Well, that messes things up. But things will work out in the end, though.
It's okay.
What happens is if you ever write a textbook and you make changes from version to version, add any new exercises at the very end. Don't add an exercise early on, okay? I'll just give you that piece of advice there. Or
Ever write a math textbook?
yeah, or alternatively, what you could do, if you want to put it earlier, then take one of the early problems out and just replace it with the new problem. Okay? But don't just add problems at the beginning and then shift all the numbers up 1 or up 2 or whatever. Okay, or maybe in the original version you can leave some blank exercises at the beginning. Those are just blank exercises in case we add more later. Or add it as a part. Add something as a part of a previous problem. Okay. So, any other questions on 4C? Okay, let's go on to, what about chapter 5? Any questions there?
Are you teaching chapter 5 today?
No, we're teaching chapter 6. We already finished chapter 5.
Okay.
So for X,
I,
you go.
oh, I was just wondering if we can have an example of how to use the Cochise inequalities.
Yeah. Well, it was used in the proof of,
Is
well,
that
the problem
mainly
is,
used for proof instead of like calculate something?
yeah, it's more used in terms of proving things.
Gotcha.
So, but I'll give you an example in a second. Okay, so Louisville's term used it. It used the case where, right here, this is the ML, and this is Cochise inequality, basically. Starting with that and ending up with that. Okay. Also, I did an exercise. Let me see, where is that? This right here, this problem right here. Suppose f is entire and f of x is less than or equal to, or then modulus of fx is less than or equal to a times the modulus of z plus b for all z's. Prove that f is a linear polynomial. Okay, so this is Cochise inequality right here. Okay, so that's another example. This right here is Cochise inequality. For, and that's n equals 2. But let me give you another example. I have to make something up really quickly. Hold on a second. So here's an example. Okay, so let's suppose f of c is less than or equal to, we'll say it's less than or equal to 5 on the disk z minus 3 equals 7. Okay, so on this right here is the disk, is a circle. I'm sorry, it's a circle centered at 3 of radius 7. Okay, so that's the disk of centered at 3 of radius 7. Okay. Instead of that one, we'll put a derivative. So what do you want? The third derivative or the fourth derivative?
Third.
Okay, the third derivative. Okay, so the third derivative, the modulus of the third derivative of f is less than or equal to 5 on this disk right here. Okay, and so the question is, find an upper bound for f of 3. In other words, what is the, no, wait a minute. Okay, hold on. I messed up. The derivative goes right here. Find an upper bound for the third derivative of f at 3. Okay, so Cochise inequality would be n factorial m over r to the n. But in this case, n is 3, right? What's m?
Is that 10?
What's that? 10?
10.
No, it's not 10. What is r? What do you think r is?
R is 7. 7 to the 3.
Yeah, 7. R is 7. And m is, what did you said 10 or did you say 5?
Oh, 5.
Yeah, okay, so this will be your m right here. And that's your r. And then here's your n is 3. Okay, so the upper bound for the third derivative would be, what is that, 6 times 5, that's 30 over 7 cubed, whatever the heck that is. So that would be an answer right there.
Okay.
Okay, another kind of problem that's along these lines would be, so let's say you have the same stuff, everything the same, and you're supposed to find an upper bound for, we'll take the third derivative, still the third derivative, but this time we're going to go 0. Okay, that's 0. Okay, so you're over here at this point. For this one, you're going to use, there's another problem, there's another thing in, so for here, what we're going to do is we're going to do a circle inside this big circle that's centered at 0, that's as large as possible. And that would be this one right here. And what radius does this circle have? Or in other words, what's this point? Well, first of all, what's this point here? This is radius 7, so that's what?
5. -5.
-4.
-4. It looks, I drew it wrong. It's actually -4.
Oh, -4.
Yeah, because all this has,
Oh, yeah,
this 7. So that means this distance here is 4, right?
yeah.
So that means that everything is the same except r is going to be 4. There's another theorem that says, it's called the maximum modulus principle. And that is that if you're holomorphic inside here, oh, I guess I need the conditions that f is being holomorphic and z minus 3 less than 8 or something. So we need a holomorphic in some open region that contains all of this and contains all the inside, basically. But there's another principle that the maximum or the minimum, if f is holomorphic on a region like this, then the maximum and minimum are both going to occur on the boundaries. The maximum and minimum of the modulus is going to occur on the boundary. So if this is less than or equal to 7, if this is less than or equal to 5 for everything on this blue boundary, then on the green boundary, since that's inside the blue boundary, that's also going to be less than or equal to 5. So that means you can use the same m, you can use the same m, but the r is going to be 4 now, because now this has radius 4. So that's 3 times 2 times 5 over 4 times 4 times 4, oh dear. One of those we just this as 15 over 32. So that'd be 15 over 32. Okay, so that's some examples of using Cochise inequalities. There's not really any good. What's that?
Oh, I wonder, for the modulus of fz less than or equals to 5, where is the point? Like, can I see it on the graph? Like, where is the maximum? Mm-hmm.
This right here?
Mm-hmm.
Well, just on this circle here, it's always less than or equal to 5. We don't know where the...
But you don't know which point is it?
Yeah, I don't know which point. Well,
Okay.
there might be less. It might just be less than 5 everywhere.
Okay.
Okay. So there's not really, in the homework, there's not really any good questions like this because they actually never covered Cochise inequality in the textbook. Cochise inequalities, other than when n equals 1. Other than when n equals 1. So, yeah. Okay. Any other questions about anything? Okay, let's move on. Oh, there's one final thing that I want to point out with chapter 5. Just sort of a concluding concept here. And that is, I like to point out this kind of situation here. Okay, so we're looking at this kind of an integral, okay, z minus z naught to the nth power over some curve gamma. Okay, and let's suppose that our z naught is some point in the complex plane, and then let's say gamma is positive orientation going around z naught, like that. Okay, so let's explore this for different values of n. So first of all, where n is greater than or equal to 0. So what's the integral going to be? Does anybody remember? And let's say that, yeah, so does anybody remember what this integral is going to be? You should be able to just say it right away.
0.
Yeah, that's 0. Because when n is greater than or equal to 0, then these are all holomorphic. This is an entire function, so the integral is going to be 0. Okay, so now case 2 is where n equals -1. Okay, so here you have this. Okay, so when n is -1, so that's z minus z naught to the -1, which is the same as 1 over. Okay, so what's the integral going to be in this case?
2 pi I.
What did you say? Did you say 2 pi I? Or did someone say 2 pi I?
Is that there?
I thought someone said that. Okay, but that's what it is. It's 2 pi I. When n is -1. Okay? And I showed you this a couple of times. And also, you could also do Cochise. There's a lot of ways you can come up with this. There's Cochise integral formula. Basically, the numerator is just the function 1. You plug a z naught in there, you're just going to get 1 still, times 2 pi I. So 2 pi I times f of z naught, but f of z naught is just 1, so it's just 2 pi I. And then you could also just like, another way you could do it, the way that I showed you how to do it is you deform this contour down to just the circle. Okay, and then you have parameterize the circle as z naught plus r e to the it and go from 0 to 2 pi. Okay, and then that comes out to 2 pi I. I've shown you how to do that before. Okay, so the third case where n is less than -1. So like you're -2 or -3 or something like that. So here you have this integral here. We'll say that's a k. Okay, so we'll say k is -n. Okay, so that's it. So you have something like this where k is greater than 2. It's 2 or greater. It could be 2, 3, or 4. We're only looking at integer values because if it's not an integer, then forget it. Okay. So does anybody remember what this integral is going to be?
Is it f of k minus 1 w?
The derivative, right?
Yeah. Derivative.
So 2 pi I times the derivative times the k minus first derivative, right? As z naught. But f of z is just 1. So the first derivative is just 0 everywhere, right?
Mm-hmm.
That's just going to be 0 then. Okay, so that's just kind of something that I wanted to point out. So it's only right here where n is -1 where you have that you get 2 pi I. Here you get 0, and here you get 0. Okay, that's a very important concept as we go into chapter 7, which will come back, and then for the rest of the semester, that this idea right here, that this is holomorphic, so that's 0, and then this one right here, you just apply Cochise integral formula, and boom, you got that. There's also going to be other things here. Hold on, I guess I should write it down correctly. Just a second, let me find it. Okay, I'm sorry about that. So this is divided by n factorial, or I'm sorry, k minus 1 factorial. Yeah, so technically you're going to have that right there. Something like that, okay?
Wait, I don't get it. So you get the same result if you put k minus 1 factorial in the denominator?
Yeah, because this right here is 0.
Okay.
That's 0 anyway. So that is not going to really change anything. But that's the formula. Because if you look at Cochise, I said Cochise integral formula was this one. it's n factorial over 2 pi I. Cochise integral formula for derivatives is this, for all values of n. So since this n plus 1 is a k, that means we have a k minus 1s here and here instead of n's like we have here. And then this goes over, this goes up to the numerator, that goes to there.